I was really surprised and very happy that I can be here and tell you something about my research, and maybe I'll start with saying a few words about myself. So I did my master in Warsaw in theoretical physics. I did my PhD in Germany, theoretical physics, or maybe a bit more applied. But this was theory, and then I came back to Poland, thinking what to do, and I came across Piotr Kostecki was working in where I work now on droplet microfluidics, and this was like for me, it was really like input to stay in science because I found it so super interesting and charming. Because this is all about droplets moving in microchannels, and when I looked at it, I was just I just got involved, and what I'm talking about now is just toys in principle. It's not like I mean, compared to Professor Grelas, it's like already applied and it's based on pure science. I mean, here I'm doing a lot of things just because it's kind of it's something that I don't understand. They try to explain, and it's really more like playing with techniques and technologies, and then thinking maybe we can use it for something. So what I will talk about today is mainly okay. So maybe finishing my story. So I did my first postdoc with Piotr Kostecki in Warsaw, and then I did my second postdoc at Princeton in the US with Howard Stone. And then I came back last year to Warsaw, and I established my small team. And now about the subject, the microfluidics. So the idea is miniaturization of a chemical lab. And this idea has been around since maybe 15 years or so. So that instead of doing reactions in microscopic flasks by manipulating this glass containers, we could use tiny droplets of size like a few hundred microns or less, and move them by flow or by other forces, and merge and use them as as reactors, so to say. And the main advantage is that maybe you can do it fully, like spontaneously at high throughput and high. I mean, you cannot do very large volumes. I mean, there are ways of increasing the throughput, but the idea is that you can, for example, scan the reaction conditions. Just instead of pipetting, you join droplets and you can do it at like kilohertz frequencies. But I'm not going to talk about this. Because my perspective on droplets is different. I'm thinking of using droplets actually to build new materials. So make something like more similar to tissues, let's say, or yeah, this is something more scalable. Because in principle, when you think of cells, they are gel like something, but they are made mainly of water. And then you have these boundaries, which are membranes, and then they form something that is made mainly of water, but it has all these properties that are very, very, very different. And many of those properties depend on how cells interact. So we have some kind of soft granular material of mechanical properties which are actually pretty complex because they depend on all these interactions of these tiny grains. So the idea is that maybe using droplets as just this kind of protocells, we can extract some information about how biological materials work. But this is not the only thing where it might be useful. Anyway, the most basic idea is that when you have two droplets of immiscible liquids, like water and oil droplets, let's say, when you bring them together, they will not merge. They will not mix because they are immiscible. So then there are a few options depending on like what we call surface energies. And this is the diagram. We have, let's say, two phases, A and B. And depending on the ratio of surface energies A and B to the new to the energy of the new phase formed in between, we can have this like one droplet like heating up the other one, or they are staying together but they are not engulfed by each other. These are called they are actually called Janus drops from this Greek god that had two phases. So I'm mainly going to focus on this case when we have complete engulfing. So when you have one drop and a tiny amount of other liquid, it will just spread around, and you have this core shell morphology. Now, when you add more, you can imagine that you have many droplets engulfed in one big drop. And now we think of this large drop as filled with some stabilizer for the droplets. So even though maybe they are of the same phase, they still don't merge. And when you decrease the amount of the volume of this engulfing droplet, at some point you have this close packed droplets which are not anymore really a liquid, but they form kind of a solid particle made of liquid segments. So this is already something that brings us closer to to tissues and all this biological stuff. And the way we approach it experimentally is by using microchannels, where we supply flow of liquids externally by using pumps or pressurized containers. This doesn't really matter. The thing is that then we supply it to channels, and we have these two immiscible phases supplied here on the so-called T-junction. So let's say this is water and this is oil, and then we have like a string of droplets flowing down a channel. And then here we supply a third phase to get this core shell structure, because there is a third phase outside. There must be something. I mean, this is not air. We could try to do it in air, but then there is a big density difference, and the droplets tend to stick to the wall, so air is not really so good. Even though doing air is also useful, but in this particular case we're using another fluid as a carrier phase. And now, to tell you about possible applications, it's not something we have done, but it's something that a lot of people is working on, and where a big part of microfluidics is going towards. So, one idea is to actually use this possibility that you can design partial structures to fabricate capsules for drug delivery. So in general, people like to do small particles because they have large surface to volume ratio, and you can release a lot of material from the surface. But you can do something more complex when you, for example, need to release two drugs from one particle. And let's say you want to release first one drug and then the other. You can put the first one in the shell and then the other in the core. And then first you have diffusion from the shell and then from the core. The problem is the centering of this stuff here. Like you can see here, this internal droplet tends to freely float around the big one. So one option is to put the other droplets around. Then you can have this kind of one droplet being in the center, surrounded by this kind of ball bearing of other droplets. You can also think of making sequential chemical reaction in different compartments of such multiple droplets. This requires further functionalization and a bit more of chemistry. We're not focused on this. The big challenge is your miniaturization and stability, because if you want to have drug delivered, for example, down this tiny capillaries, you should actually go to really single microns or maybe below. And for now, what we can do is droplets around maybe down to 50 microns. So it's still like 1 or 2 orders of magnitude more. And the second field, like independent, is micro-tissue engineering, because we can actually use the fact that these are liquid compartments, and you can put something inside that needs water. And if you think about this, you can actually put the living cells inside droplets and then assemble these droplets into something that that can be used. And one of the options is to use this kind of microscopic cell aggregates for drug testing, or like model systems for studying interactions between well-defined tissues. So we can, in principle, put different cells in different compartments and see what happens at the boundary, or how one type of cells interact with other cells. And this would be particularly useful if you, let's say, put cancer cells in one drug and then healthy cells around, because it creates a microenvironment for these cancer cells, which is just more realistic than, okay, because drug testing is already there, and people put cancer cells on Petri dish, like this 2D arrangement, which is not very realistic. They just behave differently than in actual human bodies. So people are now trying to create these microenvironments for cancer cells, particularly promising field is this personalized medicine. When you do a biopsy, take these cancer cells from a patient, and then test drugs on this cell. So this could be kind of technology enabling this, making the microtumors for drug testing. And this is what we are trying to do already. And the third thing is this physics of soft granular matter, which is what I mentioned in the very beginning, that we want to use droplets just to make physical or experimental model systems for actual tissues. And we can, for example, make these droplet aggregates and squeeze them, compress, decompress, just look at the mechanics. And this is actually a snapshot from what we did in the lab. This is just a bulk of droplets. Nice thing is that we can see everything here. We can recognize single droplets, see how they move, describe the dynamics, and so on, which is pretty difficult to do with cells. And these are super nice people that work with me. Marco is a postdoc, and Monica and Robert are PhD students, and we're quite interdisciplinary team, because Marco is a polymer chemist, Monica is a biologist, and Robert is a physicist. So it's super mixed. Okay, and this is how it actually works in reality. So you have these droplets being made on a T-junction, and then here they are encapsulated in this shell. And one can play with the amount of different fluids. So, for example, if you increase the flow rate of water, then instead of these compact clusters, you actually get this elongated chains. One can make this stability diagram, or depending on how much oil you use or how much water you use compared to oil, which is this axis, and here is the number of particles. But let's say we look at the given number of droplets, we go from this spherical-like aggregates to these elongated ones. So those are spherical packings, capillary, because capillary forces are important, and chains. And there is a big metastability for a given number of droplets, just depending on the volume fraction. This is what I just said. But interestingly, this is this is different than in the case of solid particles, because there were previously some experiments on the solid particles with drops, and they usually got just a single structure. So on one hand, it is good because you have like a higher yield of a structure that you want to get. On the other hand, we can make different structure, and we have some control parameter, which is this volume fraction. Again, this, but it's not like super precise because we have some probability distributions for different structures, but we can shift the peaks of these probability distributions depending on the volume fraction, which is short here. And here was like a little model that we devised to explain why these chains are stable. It's actually when one calculates the surface energy upon deformation of the droplets by this confining shell, it turns out that this linear configuration is locally stable, it has locally lowest energy. But then when it gets like perturbed, the structure collapses and you get this kind of compact structures. Then one can go one step further in complexity and make droplets of different volumes. So then we get something like Morse code. So we have, let's say, dots and dashes, and then depending on the sequence of dots and dashes, we can do different letters. And the thing is that different letters fall differently. Then after they exit this narrow channel to this wide chamber, they fall in different way depending on the volume fraction. And then also if we use droplets of different content, we can actually assemble them in a given configuration. So this is already something that brings us closer to the goal of like assembling this, patterning this cells or micro tissues with respect to each other. And another application of the droplets was for studying chemical communication between compartments, which in principle is maybe the basis of how a nervous system works. You have transmission of electrochemical signals between compartments. That's it. You're doing it right now. I hope so. And of course, this is super stupid problem, but well, the medium here is not, these are not neurons. So the medium that we use is aqueous, but it's a very specific reaction. Because what one wants to do when one builds a model, one wants to see something and measure something. So we use this nice oscillating reaction, which is called Guzowski reaction. It's a pretty complex reaction, but the nice thing is that it changes color in time. So you can see actually this chemical wave spreading along the substrate that you use. And here we use compartments. So, so I need to... Doesn't get darker. Can we maybe... Wait, can I switch on the light? Yeah. So we have this oscillating medium encapsulated in droplets, and we believe that the larger droplets are more active. So we put this big drop in the middle, and initially we just see random oscillations, but with time you can see that this big droplet will become like a pacemaker. So with time, the communication between the droplets is established, and now this droplet sends the signal and it spreads towards like outside. This is 30 times faster, so the reaction is pretty slow. But still, like in terms of thinking about basic, like if we want to, we will not build brain with this, okay? But this can be used as like a prototypical model system for studying information processing in chemical systems. And maybe building simple like logic gates or memory units. And you can think about design principles for such devices, and one of them is, for example, this, that if you want to have signals sent from here to here, you should order the compartments from largest to smallest. All right. And now different things. So this is what I've been doing more recently, is self-assembly of droplets in this long chain. So I already showed you the this short chains, but then if you actually properly play with the flow of this external phase, you can make infinitely long chains. And this is how it works. So the chain is not necessarily simple linear chain. You can have this periodic or not periodic faults. So you get something like this. And we think that it happens is because these chains of droplets are somehow compressed by the external flow. And then when they are compressed, they climb up this small energy barrier here. And then when this neighboring capillary bridges merge, you have sudden rearrangement. And you get here, which is like a local minimum. And then when it's further compressed, you have this second fold appearing and so on and so on. So we have this sequential folding of the linear chain to this more complex structure, which is maybe in terms of energy, when you look at this, is something like a ratchet. And this is how it looks when you look like in a time sequence, that this drop goes up, this one goes down, and then the whole thing like travels together with the flow. This is like the whole stability diagram for different structures. One can have like blobs or this kind of ordered, maybe like clusters or ordered clusters. And then when you decrease the flow of the external phase, these clusters merge into like this continuous thread. And then when we decrease, on the other hand, the volume fraction of the droplets, we effectively decrease the rate of generation of droplets, so they get stretched by the external flow into like thinner and thinner, even though this thinning is like discrete. So we have these funny structures in between, and then at some point we have like chopping of the chains into tiny segments. We focus on this, what I call N threads, where N is like actually the effective thickness of these threads. So this is a very simple model which explains what's going on. So in principle, this can be understood in terms of continuity, because we have droplets being generated at a constant rate. Let's say they enter with some translational velocity u1, but the thread, the whole thing moves constantly with some other velocity. And then if these velocities don't match, it has to be compensated by this periodic folding of the chain. So on the other hand, we know that the speed with which the whole thread moves must be related to the external flow. And and then we have this index m, so this kind of frequency of folding related to the frequency of generation and the external flow, which both depend on Q and P. Q is like the ratio of flow rates, and P is this volume fraction. And then we get this simple equation, and we can draw this diagram, which kind of qualitatively resembles what I showed you here, with these lines, slanted lines. And here, where we go from this double chains to single chains to this continuum of different structures, and then we have this finite chains here. Okay, the last thing about this is that one can actually predict how this chains fold drop by drop by applying this elastic bead model and saying that when we have some given structure, we can calculate the stress distribution, and if external flow is very weak, then we actually have increasing and increasing compression of droplets when we increase the length of the chain. So this is this compression which increases up to the inlet. So the compression is highest where the droplets enter the channel. But of course, this compression cannot increase indefinitely because everything is soft. So, so this chain must release this compressional stress. This is shown here, where you have this generation of a linear chain, and the stress, this compression grows. At some point, it reaches some threshold, and then you have rearrangement and formation of this fold, and then again, droplets are generated in a single file structure and then fold again. And by this repetitive rearrangements and stress release, we have formation of this periodic structures. Okay, so we can have periodic structure where this is a unit cell. It's like a one-dimensional crystal. But crystals can be more complicated. So you can have unit cell which is built of two different atoms, let's say. So this is one atom, and this is the second different atom, like sodium chloride. So we have 2 segments per unit cell. And actually, all information that says this sequence is given by this index m, which in turn is, in experiments, they set by the ratio of flow. And then when you choose it like this, it's given by this formula where tau is golden ratio, which is this number. Then what you get is something that is looks like it's ordered, but actually, when you can like propagate this sequence indefinitely, and it's never periodic. So this kind of stuff is called quasi-periodic. It's called quasi-periodicity or Fibonacci sequence. And this is really interesting because a lot of things in nature are related to Fibonacci sequences. Like when you look at how, for example, the seeds in sunflowers are oriented, they fall in this kind of spirals. And then when you calculate some aspect ratio in the spirals, they actually give you the golden ratio. So we have something that is, we see something that is pretty like universal in a sense that this kind of numbers are appearing also in different fields of science. But this is a model, okay? So now the question is if this is really what we see in the experiment. So this is the sequence of, so here is the length of segments. So let's say that we have these 2 types of segments, A and B, have lengths 2 and 3, and we have this repetitive, I mean, it's repetitive, but it's not periodic, just as I said. And then when you calculate autocorrelation function, it's something like this, which means that it's not decaying. Okay? It just means that you have these finite oscillations, and when correlations are like around 1, it means that you have ordered structure. Or when they are like -1, it's also ordered. Now this is what we see in experiments. It's somehow similar, but we have these fluctuations. Sometimes the segments are longer or smaller. And when you calculate autocorrelation function, it is more like close to 1 at the beginning, but then it's more like oscillating around 0. And then I thought, okay, maybe it's random. So when you do a random sequence and you calculate autocorrelation function, it actually looks more like what we see that in experiment than this quasi-periodic structure. So we think that there is just noise in experiment. And the question is how to get rid of the noise. And my idea is that, I mean, it would be really nice to have these quasi-periodic structures because they could be, it could be maybe useful, for example, in photonics. I can mention this, but I think it might be the case of a different design of the channels. But this is just results from last week, so I'll stop here. The possible application of these threads are, for example, granular electronics. So apparently there are some nice electronic features when you have lines which are not just simple continuous lines, but made of these beads. When these beads are nanoscopic, you have some quantum effects which in principle change like the conductance properties and so on. And here in this paper, okay, I can't remember the length scale, but I think it's probably around 1 micron. Okay, so it's much smaller. But they fabricated something similar. So they get these grooves in which they put particles, and they have either like single chain or double chain or something in between. But they don't really control the sequences here. So the advantage of our technique could be that we could actually control the sequences. And this was a paper published last year by actually a friend of mine who was working on the problem from a completely different perspective and independently. And what they did, they just immersed like electrified needle in a suspension of particles, and then they pulled it out. And then it turns out that because there is electric field and particles are maybe dielectric, they adhere to each other, and you can pull out this chain. And you can also pull out this kind of chains which have the substructures, or like thicker chains, depending on how fast you pull. So it seems like it's very much related to this what we have. Now, as I mentioned, you can put some stuff inside the droplets and print the droplets. This is a paper from last year from Hagan Bailey's lab in Oxford, where they use droplets, but they actually print droplets and they encapsulate cells inside. I'm not sure what they plan to use it for, but I think drug testing is a nice idea. And photonics is just a free thought, because if you think about this thread, and then if you, let's say, cast a photonic fiber around this thread, then it has some longitudinal structure. And if this structure is periodic or quasi-periodic, if you can control it, then you can actually control the photonic properties of the fiber. Now, the last part is this modeling of soft tissues by having these big clusters of droplets, where you can think about droplet-made material as like kind of a new continuum. So, and actually, there is a nice comparison to actual vertical cell aggregates, because this kind of cell aggregates has been used since maybe 25 years. People just study mechanical properties of tissues by using cell aggregates. And also, when you think about embryos, when you just have like a few, maybe up to 100 cells, and how it develops, the mechanics can actually play quite a significant role. So these are the typical experiments that people do, like Brown's and Rutgers. They compress this ball of cells, and then they look at the shape relaxation. And when you plot the deformation versus time, it's like this. This is semi-log scale, so we have exponential relaxation at late times, like straight line, but then you have faster relaxation at the beginning, which can be fitted by double exponential. Anyway, you can see that here you have two time scales, like fast and then slow relaxation. Now, the droplets can be functionalized to even further resemble cells, because we can make them adhere to each other, form these flat faces. Then when you have collection of droplets, it's good like this honeycomb. This is 2D, but in 3D is the same. And this is how we actually do it. So we make this large cluster, droplets in oil, and then you have to get rid of this oil, just to stay with this very compact, close-packed structure. And one can do it, and then the experiment looks like this. We apply the flow. Droplet enters from thin channel to a wide, and then it freely relaxes, and we can track the contour of this cluster. So if you just had a normal, simple liquid drop, it would relax back to sphere. Like normally droplet wants to be spheres because then they're most compact and they minimize surface energy. But because there are tiny, like here there is like around 10,000 droplets. We cannot see it because it's a macroscopic, here is like 1 millimeter, but there is around 1,000 droplets of 100 micron in size. So because they interact and they elastically deform, they oppose this this relaxation. And actually, when you wait, even if you wait very long, it has some plasticity. So it's more like a semi-solid material than liquid. And then if we look at the formation versus time, after subtracting this final shape, we also see double exponential. So it seems like it's a pretty universal feature for these soft granular materials that we see these two time scales. But then these two time scales are pretty scattered. Like when you look at long and short time scale, it seems like when short one grows, the long one also grows, but it's not super consistent. Cell aggregates are somewhere here. But anyway, the order of magnitude is also similar. We don't know why, because there are two orders of magnitude difference in size. Like the cells are a few microns, the droplets are more than 100 microns. But what can be done with this system is that we can do better imaging in the cells, so we can actually look through this aggregate. And then you can see the rearrangements going on inside this cluster. So we can play it again. You can see the rearrangements, like this kind of blinking or speckles. But then if you just look at the surface, so now this is the, the fluorescent image, so we just look at the surface of the aggregate. So for me it was quite surprising, but there are no rearrangements. It seems like more like a rigid shell. And this is the same drop. I mean, it's just the same drop which was squeezed back in and pushed out from the child. So we have a simple analytical theory of this elastic viscoelastic ball, assuming that there is some elasticity and viscosity of the interior and some viscosity of the surface, which also has the surface tension. And then this model actually always gives a double exponential, so it's nice. But the separation of time scales that we see in the experiment requires that the surface viscosity is much larger than this effective bulk viscosity. And why it should be like that? I mean, one hint from experiment is that because the surface seems like immobile, there is no rearrangement, so it seems like it's more rigid indeed. So, but to actually check what's going on, I did rheological measurements. So I just made a lot of droplets with this parallel device because to actually measure properties of droplet-grade material, you have to put it in the machine, but you need a few milliliters. So you have to, if I just had one channel, I would have to use it, like, have it running all day. When I have it running all day, these droplets, they might already become unstable. So I have to do it pretty quickly, so I use this kind of device, and then I have these droplets, I put it between the plates. This is actually a pretty expensive machine, maybe not like electron microscope, but it's very precise. It just makes super precise measurements of forces exerted on this on this emulsion versus displacement. And then you can get information about, for example, effective elasticity of these droplets. And what we see here is the elastic and loss modulus, which in principle we see the elastic is bigger than loss, which means that this material behaves like a solid. But then when you actually apply large deformation, make like continuous translation of one plate versus the other one, the sample starts to flow. And then you can, so it's liquid-like, and then you can measure the viscosity. And what is interesting is that here we have the shear rate, so how fast this upper plate is moving with respect to lower plate. And you can see that viscosity drops by 3 orders of magnitude when you change the shear rate. And now we did some more detailed theory, actually simulations of flow inside the viscoelastic drop. And then when one plots like the shear rate distribution inside the drop, one can see this core-shell structure, where you have high shear rates in the middle and low shear rates on the outside. So shear rates mean how much deformation you have, like local deformation. So this this actually is consistent with the assumption that we have hard shell soft core, because here we have this sheared material which is supposed to have low viscosity, and then this not sheared material on the surface, which then is pretty rigid. And then this model, the simulations also actually give double exponential relaxation. So you know that maybe there is a hint that there might be something maybe more universal in soft matter, like in these things made of grains, that when you have a cluster or aggregate, the stuff at the surface is less fluidized than the interior. So we have maybe kind of universal dynamics in soft matter. But this is the question to be answered. Of course, one has to do much more measurements and maybe study different materials and so on and so on. Okay, that's it. So this is my talk. Thank you very much.